Finishing off section 6.4 today. I'm going to look at particular kinds of questions here at the end, the last four. And these are different from what you did yesterday. We're going to find the work involved in lifting things, for instance, in this case, lifting a rope all the way to the top. Now, this rope, let's tell you some distances first. Let's say this is 20 feet and the rope weighs 1/2 a pound, a half a pound per foot. And so I want to know the work done in lifting this rope all the way to the top, right? So you're pulling it up and you get to the end, you know, there's it, you've got your whole rope. Now, this is not the correct answer. Oh, you take the weight of the rope, which is what, 10 pounds, right? 20 foot of rope at half a pound, that's 10 pounds, right? And 10 pounds lifted 20 feet, the work done should be the weight, 10 pounds, times the distance, 20 feet, which is what we did in the gorilla question right at the start. Remember, weight of gorilla, 20 feet. Why that's not correct is that as you pull that rope up, can you imagine you got to some point like here? Isn't there a lot less rope to pull up when you're halfway? Isn't the weight of the rope that you're pulling different than when it was the full rope, right? And as you take each foot, aren't you pulling up less weight of rope? So can you see that the amount, the weight, if you want to call it that, of rope changes depending on where you are in the journey from the bottom to the top? And that's kind of the adaptation we're going to deal with in these four questions. We're still going to get a force function. And what we do is we imagine a random position somewhere between the top and the bottom. And this distance, I'm going to call it x. So f of x is basically the weight of the rope. Well, if rope weighs 1/2 a pound a foot, and this distance here is x, won't the weight of the rope be a 1/2 x? Does that make sense? X feet of rope, 1/2 a pound a foot, 1/2 x pound, that's the rope. There's your guy. Once you know the force function, isn't the work done the integral from a to b of your force function dx? So far, so good? Right. Now, in this story, we have to figure out what the range of x's are going to be. Now, if you're pulling a 20-foot rope from the bottom to the top, what would be the reasonable numbers for these two? Because these represent the range of x's.
From 0 to 20, I assume?
Yes. Would you agree? From you got the end to you've got 20 feet to do. And the force function, dx. Right. At this point onwards, it doesn't matter what the story is. Isn't this just find an integral the usual way? So, power rule, add 1 to the power, divide by the new power. Evaluated at x equals 0 and x equals 20. That is 1/4 20 squared. Take away 1/4 of 0 squared, which is actually just 0. That's 400. 1/4 of 400 is 100. And the units right now are feet, pounds. You like that as a way to actually model something a little bit more realistic? Now, I can do better than just that. Can you imagine that you're pulling the rope from the ground to halfway? That's 10 feet. And you're pulling the rope from 10 feet to 20. So the work done in going from no rope left to 10, and the work that you would do from 10 feet of rope to 20. Wouldn't these two calculations represent how much to pull the rope halfway up, and the other one, how much work would be done to finish the job? Would you expect these two numbers to be 50 and 50?
No, because from 0 to 10, you're going to have more weight.
Right, so the first part of the journey, right, you're going to have more rate. Technically, this is this number, right, from 20 feet of rope to 10 feet, but you're right.
Oh, yeah.
So 1/4 x squared evaluated from 10 to 20. That's 1/4 20 squared, take away 1/4 of 10 squared. That's 100, and that's 25. So this guy is 75. Now, I could actually do that integral, but I know the answer. Isn't it going to be the rest? And the reason I know is, isn't the whole job 100? So if 75 is done in this, isn't what's left the other 25 for the second part? Now, when I look at that, isn't there 3 times as more work in the first part of the job than there is in the end of the job? Right. What's the analogy of that? Do you know if you're digging a hole, right, and you're using a shovel and you're digging a hole, isn't the first 4 feet a lot easier than the next 4 feet? Because you're digging the hole and then you're throwing the soil. Well, when you get really deep, don't you have to throw the soil a lot further, and so it's heavier duty work? I don't know if that's a good analogy, but to give you an idea that halfway doesn't mean half the work, right? It depends what you're doing during each of those parts. Well, that's version number 1. The one I've just done is very like question 12. Okay. And before I go, I just remembered something. You will be asked to find this guy here, right? The 100 foot. They will also ask you to find or to fill in this fella. Remember the Riemann sums? The guy that we've got is this guy here. So you may well have to write in 1/2 xi delta x. In pretty much every one of these questions, you'll have to do this little sigma sum. So what does it look like? See this piece here? That's the only piece that's going to change. And this piece here is your force function. Now, when we write it, we call it x 1/2 x. When you do it in sigma notation, that basically means each of the little baby x's that you would use to do the integral. So that becomes that, okay? So when you're doing the funny sigma things, well, you just put your force function in here, but put a little xi instead of x, and it's done. If I had my way, I would take the sigma out because it doesn't actually bring much, I think, anyway, to the process. It's much easier the way I've shown you, I believe. So, second version of the story, I'll change the numbers a little bit. There is a 10-pound weight, and it's attached to 40 feet of rope. There's my little guy. Pretend that's not there, right? And we would like to know how much work is done in lifting a 10-pound weight 40 feet in the air when the rope weighs 2 pounds per foot. So this rope's probably a steel chain now, right? It's not much of a rope. Right, 2 pounds a foot's pretty heavy, right? So it's a big chain. You're lifting a 10-pound weight using rope that weighs 2 pounds a foot.
Mom is sleeping. Be quiet. Yeah, what?
I will mute you so that you can have that conversation on your own. Here we go. So let's do the construction of the force function. What you kind of do here, or the way I look at it is, I imagine a random part of the journey. And this distance from here to here is going to be the x. So far, so good? Now, the force function is basically, at that point, what is the total weight I'm pulling? Well, isn't it made up of the rope plus, I'll call it a rock, right? Isn't the rock 10 pounds all the time? It's 10 pounds when you started pulling it. It's still 10 pounds when you get it to the top. Fixed. The rope, on the other hand, is 2 pounds a foot. So if this distance is x, won't the rope weigh 2x? Are you happy about how I constructed the force function? Doing this little imaginary somewhere along the journey called x. Which means that we can now do the work done. It's going to be the integral from a to b of the force function. It's going to be the integral from 0, the bottom, to 40. Agreed? And the force function is that. Are you comfortable with how I constructed the force function and now using it to find the work done? Are we good with that? Okay, so add 1 to the power, divide by the new power. Evaluate it at 0 up to 40.
Is it x squared? Not cubed?
Thank you. Whoa. Well caught. X squared, right? Add 1 to the power, divide by new power. Don't know what I was thinking of when I said that. So it's going to make it a little bit easier to calculate as well, because it's going to be 40 squared plus 10 lots of 40. Can I just tell you that that's going to be take away 0 without writing it down? You know, you plug 0 in here, it's going to get you 0. So 1600 plus another 400, 2000 foot-pounds. Right, now I've done this question, couldn't you change the rope to be 3 pounds a foot, or 1/4 a pound of the foot, or whatever you like? And couldn't you make the rock 200 pounds or 3 pounds? And couldn't you make the distance that you're pulling it up 200 feet or 2 feet? Because won't they just change specific pieces, but not the process to any great extent? So with this model, can't you model any object that you're pulling up a certain distance using a rope of any weight that the rope happens to be, right? Is the rope 4 pounds a foot, or is it, you know, half a pound a foot, whatever it might be? Okay, then I'm going to give you a shot at that. There's my picture. This is 15 feet. £100 and you're going to lift it. $15 feet, and the rope, probably a chain, is £5 per foot. So your job, find the work done in lifting a £100 rock a distance of 15 feet using a rope that weighs £5 per foot. And I'm giving you 2 minutes to do that. No rush, no pressure. Okay, let's get this show on the road. What is the force function in this story then? What's the rope plus rock look like?
I got 5x plus 100.
I agree. That's what I would have got. And so the work done is going to be the integral from, would you agree, 0 to 15? That's where those numbers go. The force function. So let's see what that looks like. 5 upon 2x squared plus 100x, evaluated at 0 and at 15. That's 5 upon 2, 15 squared, plus 100 times 15. Oh, take away a whole load of nothings. That's 225, 225, 1,000, 1125 over 2 plus 1,500. I make that 4,125 over 2, but I'm doing that in my head.
Yeah, I got 2062.5.
That's what I
Which is the same thing. So we're both correct. Divide that by 2 and you should get that.
Yeah.
Now I'm about to give you another question, but I won't take it to the end. I just want to show you a little quick that I haven't seen yet. So let's suppose that in this story, it's 20 meters. and that this fella weighs 10 kilograms. And we're using a rope. And the rope is 1/2 of a kilogram per meter. Now, the only major real difference in this story, I should say G there, the only main difference in this story isn't it metric, it's meters and kilograms, not feet and pound. So you might think, I wonder if that makes any difference at all. Because it doesn't make any difference when you did Hooke's law. Remember when you did the springs, it could be feet, inches, don't really matter, right? Or it could be meters and centimeters. As long as you got the units, you were fine. You didn't need to take in that magic 9.8, right? But it does matter in this question. It's going to be the rope plus the rock. Nothing major. The rope is 1/2 times that. So what's that going to be? 1/2 x. Imagine your little guy like this. 1/2 x. The rock is 10 kilograms. Everything is fine. Now, if the units were pounds, this would be the answer. This is the guy I would use. But it's not. It's in kilograms. So here is the kicker in the tail. What do you multiply this by to take into account that you're working in metric?
Is it like that 9.8 number?
Yeah.
9.81.
Well, WebAssign wants you to use 9.8, but 9.8 one's more accurate. So you don't need to put the 9.8 when you're doing springs and Hooke's law. You do need to put in the 9.8 if a gorilla is in kilograms climbing up a 40-meter tree. You do need to use the 9.8 if you're pulling a kilogram weight up a cliff in meters. That little 9.8 is the killer, right? If you don't have it in here, your answer will be 9.8 times smaller than it should be, because we have to take into gravitational constant when we do metric. And that's to do with the units of work. The units of work are foot pounds. But when it's metric, the units of work are joules, and joules has the gravitational constant 9.8 in it, right? So it's a quirk in this process. But I mean, you can do it right now. If you did, you'd get 4.9x add 98. So this is the guy that you would use in your integral. So it's a little bit clunkier because of that, but that's what you do. Any questions about that little kink? If you do metric, remember the 9.8. Apart from that, do exactly what you would have done. Are we good? Right. There's one last question and then we can talk about the test. Well, this guy is the hardest combination. Here's my building. Here's my little guy. Here's a rope. And at the bottom, I'm going to have a bucket. I think it's a bucket. It doesn't matter what it is. I'll call it a bucket anyway. It's a bucket. And this bucket weighs 10 kilograms. Inside this bucket, there's some water. And the water weighs 30 kilograms. And the height is going to be 20 meters. So far, so good, right? So you might think, I just need to remember that 9.8 and everybody's happy. Well, let's tell you some other things. The rope weighs half a pound. Oops, whoa. The rope weighs half a kilogram per meter. Well, you'd need to know that anyway. And now the thing that makes this question really ugly. This bucket has a hole in it. And as you're lifting the bucket of water to the top, the water is pouring out. And it is pouring out in such a way that when you reach the top, it's empty. The last drop of water has just fallen out. Now, what that means is that we now have to take into account that isn't the water also going to be a variable weight depending on where you are on the journey? Great. So let's imagine that we're at a random spot X meters from the top. And now what we have to do is we have to create the force function for this entire story. Well, the way I look at it is that there is a rope, there's a bucket, and there's water. Would you agree at any given point in time, those three added together is essentially it. Now, once I get this answer, I'm going to have to stick that ugly 9.8 on the outside, but don't want to do that right now because it just confuses things, right? I'm still going to get this total weight, but then times 9.8 because it's metric. So moving on. The rope weighs half a kilogram a meter. If this is X meters, won't the rope weigh a half X? We've done ones like that before. Great. Isn't the bucket, just the metal bucket itself, isn't it 10 kilograms at the bottom and it's still 10 kilograms at the top, right? The bucket's not going to change its weight. And now the hardest one to calculate. What's the weight of the water at this position?
Would it be 30x? Not sure.
Right, we're not sure. So we have to figure out what it is. By the way, it's not what you said, but that's a reasonable assumption that it might be. If there's 30 kilograms of water and this is 20 meters, then the rate of loss, right, how much water you're losing, won't it be 30 divided by 20, which is what, 1.5 kilograms per meter? In other words, every meter that you move, won't you lose 1.5 kilograms of water? Right. You have 20 meters and 30 kilograms of water to lose. You're going to have to lose 1.5 kilo of water so that in the entire 20-meter journey, you'll lose it all, right? Now, that's just part of what I need to know. I need to know that distance in terms of X. The total distance is 20, and this is X. So what's this distance? 20, this piece is X. What's that one?
20 minus x.
Agreed. Now, at this point in space, haven't you raised it 20 minus X? So how much water have you lost? You have lost 20 minus X meters at 1.5. I probably have stuck the 1.5 here. So I'm going to call that nothing 0.5x. I'm going to call this 10. That guy I'm going to call 30. This guy I'm going to call 1.5x. This and this gets me 40. This and this gets me negative x. And I now have my force function. Now, if all the things that we were talking about here were in pounds and in feet, would it not be the final answer? But since it's in kilograms and meters, I'm going to stick the 9.8 in now. Remember the gravitational constant issue. So the force function that we are going to use is 9.8 times 40, which is 392, take away 9.8x. So the work done is the integral from the bottom to the top, 0 to 20, of 392 take away 9.8x. That's 392x. Add 1 to the power, divide by the new power, that gets you 4.9. Plug in 20. Take away a whole load of nothings. Almost done. 392 times 20. Take away 4.9 times 20 squared. And the answer that I get is 5880 joules. So the ultimate version of this question is a bucket with water that is leaking in metric. You can't get any harder combination than those things. Now that I've set this up, couldn't I change that to 40 meters? But if I changed it to 40 meters, wouldn't the rate of loss also have to change? But you could adapt it for any length. Couldn't I tell you that there was 82 kilograms of water? Couldn't you adjust it if that's the only thing I changed? So each little piece could be changed, but the process of how I did it will still be the same. Right? The process is the same. The details might be different, but not the way you do it. And that's what you want to try and get out of this. It's not the specific numbers so much as the process he did. Right? Have you noticed it's always imaginary? Imagine that you're at some value, oops, bring this down a bit, some value X from the top. And imagine what the total weight of what would be happening at that point. And each bit, you then figure out what it is in terms of X if it needs to. If it's metric, stick a 9.8. If it's not, leave that out. And then the final work is just going to be bottom to top of your force function. And that's, to me, is the process. Any questions? It's a lot to take in as your last guy. Are we good? Okay, so for the time that we've got left, I would like to talk a little bit more about your second test. As soon as I close off some windows. And I'll pop it over here. Okay, let's go away. I've got a window opening I don't want to open. Go away. You know, if I had a brain, I'd be dangerous. You ever heard that saying? We have some really cool sayings in Scotland that I don't hear in America. Here's one. If you get really annoyed at someone, you'll say to them, pick a window, you're leaving. We are kind of violent people. Not that I'm that violent. Right, I mean, nobody here is frightened of me, right? You know I'm a big teddy bear, right? Wouldn't hurt a fly. Now, get myself back to what we were talking about. I'm just getting this thing set up if I can. Where the heck is my little student view thing that I want to use? Okay, let me click on this. Okay, we got it. I found it. Yeah, I'll make it a little bit bigger.
You can't see your screen.
Yes, I understand. You will in a few seconds, but yes, you're right, you can. Okay, let's show you my screen now. I think the short way of describing what's going to happen is it's exactly the same as the first test. You're going to turn up at 1 o'clock, and at 1 minute past 1, your test will appear in WebAssign. And your test, the one that you're interested in doing, you've got 50 minutes. Well, essentially you've got an hour. And then you have to get it uploaded into Canvas by 2:30. Right. Now, what I have here is basic summary. Hopefully this will work. Looks like it's working, of what you need to do, right? So our test is going to cover these topics. The substitution rule part 2. So you're going to get a question on the harder substitution rules. That's the ones that aren't obvious, or the ones that have an X left over and you have to deal with it, right? You're then going to get the area between two curves, you know, f of x, take away g of x, that kind of thing. Volumes using disks and volumes using shells, right? Volumes of rotation, and work. So you can see that there's basically, what, 5 sections here? 5 questions, 1 from each section. Anything you're not sure about? Homework is due this Sunday, and it's up to and including 6-4. What else do you need to know? Looks good. Okay. Well, when you finish doing your test, don't you click on, hopefully this will be working, and submit your assignment. And it has to be in by 2:30. Desmos is your friend, you know, especially in some of the shapes where it's very difficult to sketch them. You want to be able to sketch them. Desmos will be a very good tool for you to use, and you're allowed to use it. Right? Make sure that you show me as much working as you can. Now, I know in homework questions you can cut corners because there's a lot of questions the same, and if you know what to do it, you do a lot in your head, and I can understand that. But when you're doing a test question and there's only 5, it's much better if I see everything in case. I can't remember what I did, but I think I did something like, didn't I take something and I turned it into 2/3 x cubed and it should have just been x squared? That was just careless. But at least you would have seen my working if you were me, right? And you'd say, oh, duh, he's just made a silly mistake there, right? But if I don't see anything, then that's not good news, because then it's just wrong and I don't know why. Everything else should be there or thereabouts, right? Your usual class stuff. And leave student view. Right. I'm always frightened when students, oops, I didn't really mean that. I'm always frightened when students don't ask me questions, because it means one of 2 things. I've answered everything and that's good. Or you don't have a clue what's going on and you don't even know where to start. So I'm going to go with the first assumption. that for the most part, you know what the heck is going on and you know what's expected of you, right? And if you are anybody who belongs in that second group, when I say bye-bye in 2 minutes from now, you will stay behind and say, can you go over that again? Because I don't have a clue. Okay. Well, say hi and bye-bye. I'll see you on Monday. Anybody who wants to hang about to ask questions, I'll be here.
Thank you.
Thank you.
Bye-bye.
Thank you. All right, I have a quick question about the homework.
That's fine. That's a good thing to wait for. Okay, give me a second just to clear off the paper. Right, what is it you got?
It's for the homework for 6.3.
Uh-huh.
In question number 9, it says, it basically gives you an equation y is equal to negative x squared plus 10x minus 21, and y is equal to 0, and then rotated about the x-axis, and it says you can find the volume by any method.
So you can choose the disk or the shell method, essentially.
Though
Right.
I've tried it 2 times and I got it wrong. I'm not sure if it's my method or my math.
Okay.
My algebra.
Did you sketch negative x squared plus 10x minus 21 in Desmos?
Yes.
Right. I'm assuming, and you can tell me, I'll draw my picture of what I've got, if it looked kind of sort of like this fella here. Did it look something like that?
Yes.
And you're being asked, because of the y equals 0, you're only going to rotate this piece. Did you realize that?
Yes.
Okay, so I need to know this number and this number. I'm 90% sure that the numbers are 3 and 7.
Yes.
Okay, so this one to me would work really well if you were looking at it in terms of the disk method. So the volume would be the integral from 3 to 7 pi the function squared dx. So it's a single function, works really well. And that would be, stick the pi out here. Yikes, a negative x squared plus a 10x take away 21 squared. That's not pretty, but I need to FOIL that out.
Okay.
You're typically, I'm going to do it in a separate piece of paper. Typically you FOIL with a bracket with 2 things times another bracket with 2 things, but you can actually do the process for anything that you possibly want. So let me show you how that would work. I can't call it FOIL anymore because there's too many things, and that guy there is the first one. So why don't I just call them number 1? Number 1, you get x to the 4. Same start guy, number 2. You get negative x squared times that is what, negative 10x cubed. And number 1 times this guy gets you 3. And negative x squared times that gets you plus 21x squared. And then you start with this guy and you go, that guy times that guy, I guess we call him number 4. And that's going to be negative 10x cubed. And the pictures are getting messy. So that guy times that guy is 100x squared. And that guy times that guy is negative 210x. And then this fella, this one times this one is plus 21x squared. This one times this one is take away 210x. And this one times this one is positive whatever 21 squared is.
440 something.
441, yeah. Now, I haven't quite got to where the answer goes because there's some tidying up here. I can only see 1x to the 4. I get a negative 10 here. I get another negative 10 here. So that's going to get me negative 20 of those. I've got a 21, 100, and another 21. So that's going to get me 142 x squareds. I then have this fella and this fella, which is going to get me negative 410x. And finally, I finish with 441. I mean, that's a heck of a lot of work, but are you comfortable with what I needed to do?
Yes.
Right. So we now return to here, and our volume is going to be pi, the integral from 3 to 7 of all of these guys.
Okay.
Now I'll just take it one more step and then give up. It's 1/5 x to the 5. Take away, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. I don't think that works, so I'll just call it that. 205x squared plus 441 x's. And just evaluate it at 3 and at 7. And 2 days later, you'll have a number.
Okay. All right.
I don't know if you were with the process until you got to here and then things went astray, or you didn't get to there.
I think I got to, I think I just misplaced some negatives
Okay, well, don't
when I was
don't
multiplying now. I was just wondering if there was like a better, different method, because I chose that method too. And
the other alternate method would be to do a shell method. But if you do a shell method rotating about the x, doesn't this equation need to be rewritten as x equals a function of y? And that's a non-starter.
Yeah.
So you didn't have a choice.
Okay. Awesome. I'll have just to do the algebra one more time.
Right. Be careful, because don't guarantee that this is right. It's what I believe to be right, but strange as it may seem, I have been known to do things wrong. So always bear that in mind. Right. Who's next in my list of questions? You're welcome. Anybody got a question?
I do, but I'm not necessarily next.
Okay.
Okay.
That doesn't matter. You can
Well, it may be a question that you doesn't want to share with everybody else, and I
don't mind
understand.
sharing this one.
Okay, go for it.
Hey, so I left, but then I realized I don't understand the springs very well at all.
Okay. So,
like every time I do a spring question, I'm like struggle through it and maybe get it correct, maybe on the third try.
right.
So if the work required to stretch a spring is 3 feet, so 3 feet beyond its length is 15 foot-pounds.
Right. Okay. So the work required to do an X value of 3 feet is what was that number for the work?
15 foot-pounds.
15 foot-pounds. So you basically told me the work is this, and the X is 3 feet, right?
Yeah.
And we need to find, no matter what type of information they give us, we need to find K. For springs, the force function is Kx. So if we can find out who K is, we can answer anything else that comes after that. Because after that, there's probably going to be a question about how much work is done to do this, or how much work will it take to do that. So we'll pause at this point. Now, there are 2 versions of this question. This is the hardest version. The easier version would be, they would tell me what the force was, and they tell me who X was. And in that question, if that's the information, this would be 10, this would be K, this would be 5, and we could figure out that K was 2. And you can do it almost in your head. But that's when they tell you a force of 10 newtons is required to move it 5 meters beyond its natural length. In this case, we're being given the work. So that means my starting point is going to look like this. And you might say, well, how do I know it? The work is 15. How do I know it's 0 to 3? You're stretching it 3 feet beyond its natural length. So 0 to 3 is stretching it 3 feet beyond its natural length. Kx, because that's the force function, dx. Now, if you integrate kx, and just think of k as 5 or 10, it's still the power rule, isn't it? Add 1 to the power and divide by the new power. And we're going to evaluate that at 0 and at 3. And we're being told that it's 15 when we're finished. So here goes. Plug in 3 here. You get k upon 2, 3 squared. Take away a whole load of nothings. So I have that, 9 over 2k. Now I can find k. What should I do to both sides to find k?
Multiply by 2.
Well, okay, that'll get us part of the way there. What do I do now?
Divide by 9.
Okay, and probably simplify it while we're at it. 10/3. Which means we now have, for this spring, the force function. Now, once you know that guy, you can answer any question you like. So if it says how much work is required to, I mean, they'll have a second part to it. So what is the second part? How much work?
They need to stretch it to 27 inches.
Okay, you want to stretch it 27. So the work is going to be from the start, I'm assuming. 27 inches is not really the number I'm going to use. I'm going to turn it into feet, or at least try my best.
Okay.
It's 2.25 feet. And I'm going to do it with my force function. So it's going to be add 1 to the power and divide by the new power, which gets you that. You're going to evaluate it at 0 and at 2 feet, 0.25. That's going to be 5/3, 2.25 squared, take away a whole load of nothings. Time for the calculator. 5 divided by 3, excuse me. Oops, try that again. 5 divided by 3 times 2.25 squared. That's an answer, but I'm going to convert it into fractions because I think I could do it. As an exact value, it's 135 over 16, or as a decimal, it's that guy. But the key is to find the missing k.
So as soon as you find fx equals 10 over 3x, that basically means that you have 10 over 3 pounds of force per every.
Well, the k, the units of k, I'm not sure what they are. I just think of that 10 over 3 as being a number that is how hard it is to shift that spring, how hard it is to stretch it. Okay. So a really big number, it's like 500, and for a slinky, it's 0.2. But okay. I don't think I could tell you any more than that. There's probably some weird units, like if it was made out of high tungsten steel, it would be 82, but if it was made out of copper, it would be 5, you know, and each metal that you make the exact same spring out of, the key would change depending on flexibility and so on.
Okay.
So I just think of it as just a number that is useful in how hard it is to, you know, stretch that spring.
Yeah, and they definitely they switched feet and inches on me, didn't they?
Right, and remember that it's feet in pounds and it's meters in kilograms, and that also is important when you're when you're doing any of the other calculations, that you keep your units. But did you notice in this question, although it was feet and pounds, but if it was the same kind of question, but it was like 15 joules and 3 meters, right? If they'd made it metric, you do not need to do the 9.8 thing. When you do springs, 9.8 isn't necessary. And one of the reasons it's not necessary, it's contained inside that 10/3. It's just stuck inside it with everything else. So you don't need to fix it. But you do need to fix the 9.8 when a metric gorilla is climbing a 20-meter tree. And you need the 9.8 when you're pulling buckets up 40-meter buildings, right? So remember the 9.8 in the metric buildings and the metric gorillas, but it doesn't appear anywhere else.
Okay, thank you. And I'm just going to stick around to watch the next questions because
That's totally fine. Who's next? Victoria, you got some?
Yeah, so this is for the substitution rules, part 2.
Okay, you're right. Give me the guy you're trying to do.
So this was number 3 for my homework. And
Okay.
it was mostly related to how to kind of figure out how to see like when it goes into absolute value, because some of the like natural logs, some of the answers would switch back and forth between value.
Yeah.
But I just didn't know how to like recognize when it would go back and forth between that, because I could give you my example.
Yeah, let's do that, and I can talk about it with a concrete example in front of me. I know what you're getting at.
Yeah.
Excuse me. You won't like my answer, by the way, when I give it to you. But my answer is going to be easy, so you'll like that part.
Okay. Okay, so it's just a definite integral. So sine of 2x divided by 28 plus cosine squared of x dx.
Oh, that one doesn't have a log in it. Oh, it does.
Take
it back. Yeah, right. It does. It does. I take it back. What are the limits of integration? Does this indefinite? Does it have limits?
Yeah, it just doesn't. It doesn't.
That's fine. Okay. So in this case, the u sub is the entire bottom. Okay. Now, I'm going to rewrite cos squared x like that. And the reason why I write it that way is it should make it a little bit easier to see what its derivative looks like, because this is in fact a chain rule derivative, right? A derivative that uses chain rules. So we have du by dx. That'll get you nothing. This guy here will get you 2 lots of cosine x to the power of 1 times the derivative of cosine x, which is negative sine x. So du by dx is negative 2 sine x cosine x. And now a trig identity. What is 2 sine x cosine x the same as?
What was it? 2 sine x cosine x?
2 sine x cosine x. What is it the same thing as?
Oh, is it negative cosine?
Hmm?
Oh,
At it.
Oh, a sine x.
Right? So it's the sine of 2x. And the reason I'm doing that is, hopefully it'll be a little bit more obvious in a second, is this guy. And then when we isolate it, we get this. So if you didn't know that this guy could be written like that guy, then you probably wouldn't be able to do more to the question. That would be the end of the question for you. Now, let's see what this guy looks like. We have a sine of 2x over a u times negative 1 over the sine of 2x du. And just what we want has happened. And now we're left with this guy. So far, so good. Now, you want to integrate this guy. Isn't it negative the natural log of u?
Yeah, it is. I think what kind of
With a
got
C.
messed up with this question is in the example video was they just stopped at the u sub for they just stopped at 2 sine x cosine x and didn't give the
What
rest
it
of the
became.
u sub.
Now, there's
Yeah.
another issue that you mentioned that's coming up in a few moments here. If I return back to the original, which is this guy, that is the final answer, right? In some questions with logs, you have absolute values around things. And in other answers involving logs, you don't have absolute values. And I believe you were asking me, you know, what's going on there? Why do some answers have absolute values and why do other answers not, right? So here is my answer to that question. If the thing inside the log is guaranteed to be positive, you do not need absolute values around it. The reason you need absolute values around some, but not all, is that in some situations, this expression might be negative sometimes. And the absolute value is just to cover it. And there's a good reason for it. You know, you can't find the natural log of any negative number. It's a bit like somebody saying the square root of -1 and expecting a real value, right? Now, the bad part of that, that's the easy part, right? The easy part is if the thing inside the log could be negative, stick an absolute value around it and you're fine. Now, here's the awkward part of the answer. They don't always do that. So technically, you're going to get some answers where they should have put the absolute value, but they didn't. And then other questions where they should and they did. And there is no rhyme nor reason that I found to why sometimes they do and sometimes they don't. If you're going to do the rule that I just said, be consistent. I don't know why. Maybe it's WebAssign, right? It's software. Software's not the most intelligent thing. If the guy who programmed it didn't factor in rules about when absolute values should be used in logs or not, or he put in a bad rule that didn't work all the time, that might be the reason, but that's made up. So the quick, easy answer is if it's a negative inside, if it could be negative inside, make it an absolute. Otherwise, you don't need it.
So it only pertains to natural logs then?
Yeah.
Oh, okay. That's awesome. Thank you.
Okay. Where are we off to next? If we are off to anywhere next.
I have a question about like the volume of rotation.
Okay, what you got?
I'm a little confused about like the equations that you use to get them. Like, for like the x-axis and y-axis, are they always like opposite or?
I'm not sure what you mean by opposite. The answer could be
I mean,
yes.
like if you're rotating on the around the x-axis, is it always in terms of like f of y or?
Okay,
just...
right. There are two distinct methods. That's part of the problem. There's a method called the disk method, which I believe is 6.2. And there's the other one called the shell method, which is 6.3. In the disk method, if you are rotating about the x-axis, then your formula for the volume has x's in it. Right? It's all to do with x's. So it could be pi f of x squared, but there's also pi f of x squared take away g of x squared, right? But everything has x's, right?
Okay.
So when you rotate about the x, you get that. When you rotate the shape about the y-axis, then everything has y's in it. And that's the rule for finding volumes using the disk method.
Okay.
Now, where the confusion arises, if you use the shell method and you rotate something about the x-axis, everything is in terms of y. You see it switches.
Mm-hmm.
And when you rotate about the y-axis, everything is in terms of x's. So the rule isn't if you rotate about the x's, everything's x's, and if you rotate about the y, everything's y's.
Okay.
It depends on which method you're using, what the rule is. And just to add to confusion, isn't the rule the opposite depending on the method? Right? So be clear in your brain, am I doing a disk method or am I doing a shell method?
Okay.
If you're doing a shell method, it's going to be a 2 pi y kind of f of y looked at, right? If you're doing a disk method, won't it be a pi f of x squared kind of look? Right? Even the formulas are different looking. Does that help?
I think so.
Okay, let me give you a practical example of this then. Suppose I wanted to rotate y equals x cubed from x equals 1 to x equals 3, and I wanted to rotate it about the x-axis. And I told you that we were going to do it with the disk method. Okay, so you want to set up what the integral would look like. It's pi f of x squared dx, and the range would be from 1 to 3. Since it's a disk method and it's rotating about the x-axis, do you see how my formula has x's in it?
Mm-hmm.
And the limits of integration are in terms of x values. In this particular question, it would be 1 to 3 pi x cubed all squared dx.
Okay.
Now, if this question had been, actually I should have drawn my x cubed a little bit nicer, but I can do it in my next one. Yeah, that's what y equals x cubed really looks like, right? If this question had been not a disk method, but a shell method, and they asked you to rotate it about the x-axis, which is totally doable, right? And they wanted you to do it from 0 to 8. When you take that shape, will my formula have x's in it or will my formula have y's in it?
Wise.
And when you do the equation, won't this be rewritten as x equals the cube root of y? And won't my formula be 2 pi y f of y with some stuff, right? So it's going to be 2 pi y, the cube root of y, which I would do that to. Do you see that the process and the equations are quite different looking, and the variables are definitely opposites of each other? So that's the kind of thing you've got to have in your brain. Ask yourself right off the bat, is it a disk method, in which case follow this rule? Am I doing it as a shell method, which means do it this way? And if you get a question that says, pick any method you like, well, I guess pick one and see if you can make it work. In some questions, you can find it using both methods. They both work. But more often than not, one method can work really well and the other doesn't work at all.
Mm. Is there like an easy way to tell, or just pick one and hope it works?
Well, pick one and hope it works definitely is a technique, which you can find out after about 3 minutes it isn't going to happen. But here's a simple way of telling. This guy is good to go if you're going to use x's, agreed?
Mm-hmm.
If I had to turn this into x equals a function of y, would you realize that that isn't going to happen?
Ah, yeah.
And that tells me whether I can use x's or y's. And that's how I would be able to decide disk or shell method.
Okay.
So that would be one way to tell. But sometimes you just try it and no, this isn't going anywhere I want to be. In which case, you throw that piece of paper away and you do the other one. And since there's only two methods, it's not a big deal, right? You spent a few minutes, but you know, no biggie.
Okay.
Evan, what you got?
All right, I'm out of here. Thank you.
Oh, bye-bye. Anya, are you finished for today?
Yeah, thanks.
Okay, you're
Have a nice
welcome.
day.
You too. Bye-bye.